Seyed Amirfakhri is an assistant professor in the Department of Paper Science and Chemical Engineering at University of Wisconsin, Stevens Point. Seyed, thank you so much for taking the time today.
Yeah, thank you so much for having me today and just talking about my research and some recent publication. Yeah, sure.
Well, to start, I'd love to just ask, how are nanomaterials currently used in society?
That's a very great question. Nanomaterials normally used everywhere. So if, for example, if you check the sunscreen, normally they have, titanium oxide, and this titanium oxide, nanoparticles, or zinc oxide, one of these two materials, they normally, protect, our skin for UV, radiation. Yeah, or for example, if you check, the nanosilver, particles, they use as, anti, bacterial, materials. So they are everywhere, I mean, if we check, our daily life, we can find them, in everywhere. So they can find them in electronic devices, in food packaging, in, let's say, everywhere.
Yeah. But so how can nanomaterials be used for things like heat sinks and water and wastewater treatment and renewable energy?
That's a very great question. In heat sinks, normally all, electronic devices produce, heat. So we need to remove this heat to keep, the temperature low. For example, if, we don't remove, the heat generated in cell phones, temperature goes beyond, let's say 40, 45, and this is, dangerous, for our body. So we normally use, heat sink to remove, this heat from, laptops, from, cell phones. So one of the main characteristics of a good heat sink is high thermal conductivity. So the higher thermal conductivity, the faster heat, rejection from, electronic devices. So nanomaterials normally provide higher thermal, conductivity to improve this specification, at heat sinks, to improve, the heat rejection, speed from, electronic devices. In water and wastewater treatment processes, they use to remove different pollutants, from water, from wastewater, from air. Why? Because they provide, high specific surface area. And higher specific surface area means, higher, removal rate. In, let's say, renewable energies, nanomaterials used for different, applications. For example, in fuel cells, they used to increase the reaction rate on, cathode sides. And then the higher reaction rate means, the higher production rate of, hydrogen in, fuel cells. Or let's say, electricity, sorry, higher, reaction rate, for oxygen and hydrogen, and then higher, electricity generation. Or they can be used, in, energy storage devices, to just, store energy. So yeah, these are some examples for application of this material in these three different fields.
Yeah. But so how difficult is it to work with nanomaterials? Is it labor and energy intensive?
Uh, Yeah, generally it depends, to the type of, nanomaterials, or let's say the application of, nanomaterials. Generally speaking, yeah, they are energy, intensive. For example, graphene is a famous, nanomaterials. Production of nanomaterial by chemical vapor deposition. We have, different methods for, graphene production. So chemical vapor deposition is one of these, methods. It normally needs temperature beyond 1,000 degrees centigrade, which is a huge, temperature. Moreover, we need to use, control atmosphere. We need to use methane, for example, so this increase, the, let's say, energy required, for the process, moreover, the safety of the, process. So, yeah, generally they are, energy intensive and they need, a specific, let's say, a procedure or, other methods for, production of graphene. They probably need, they normally need high chemical, for example, they need a high, let's say, huge amounts of sulfuric acid, other, chemicals to produce, this material. And one of the main problem with the nanomaterials is high production cost that relates, to this, uh, production conditions.
Hmm. So what are the advantages of nanomaterials?
This is, let's say, the critical question in this field. Okay, we pay, let's say, this huge cost. We need, a specific, temperature, high temperature, very, a specific safety procedure. What is the advantages, or what are the advantages of these, materials? To explain this one, we need to just go over quickly on some simple, and basic engineering equations. So in heat transfer, normally the heat transfer rate is a function of surface area. So if you have two, let's say, system with everything is the same temperatures, all parameters are the same, and the one of them has higher, a specific surface area or a higher, surface area. Let's say, for example, these two, systems. So this heat transfer rate from this system with higher surface area is higher.
Hmm.
So we prefer to increase, the surface area to increase, the heat transfer rate. In reaction engineering, I explained it, in the previous, question. We use nanomaterials in cathode side of fuel cells to increase the reaction rate. So in reaction engineering, the higher surface area means, the higher, reaction rate. So in adsorption, to remove different pollutants, from the water, wastewater, the higher surface area means, the higher, adsorption rate. Why? Because we have more sites, to remove pollutant. So surface area is a critical parameter. Now, in nanomaterials, we have, a specific parameter, which is called, a specific surface area. What is the specific surface area? A specific surface area is area per unit mass or volume of a substance. We normally use, unit mass. For example, we reported it in meter square per gram. So the higher a specific surface area means that you use the same, weight of material. But when a specific surface area increases, you have more specific, more surface area. So one of the main, a specification of nanomaterial is high specific surface area. So high specific surface area means higher heat transfer rate, higher reaction rate, higher adsorption rate. So everything increases. Now, what's the benefit of using, let's say, ultimate benefit of using this material? If you have two materials with the, let's say, different, specific surface area, and you have a constant heat transfer rate or high constant adsorption rate, your equipment size decreases. When equipment size decreases, this means, the lower, capital cost, lower, let's say, operating costs. So this is why we work, on, nanomaterials. So nanomaterials provide, high specific surface area, and then high specific surface area means, high reaction rate, high, heat transfer rate, and high, adsorption rate. Just as an example, the specific surface area of single layer graphene is about 2,500 meter square per gram, meaning that the basketball field area is around 440 meter square, meaning that with 1 gram of, graphene, you can cover more than 5 basketball fields. This is a huge, area, Craig. So this is why we try to, produce, nanomaterials and then to improve, the specific surface area and use them, for different applications.
Hmm. So, what are the challenges? We talked about the advantages. What are the challenges associated with nanomaterials?
So yeah, that's a that's a normally, that's a very good question. Normally they are expensive materials.
Hmm.
Why? I explain, they need, high temperature. Let's say, they are energy intensive. They need, chemicals. And one of the main challenges of using, nanomaterials is, their cost. Um, so energy, they need, high energy, for production of these materials. And the other thing is that we know to some extent about the short, let's say, term effects of these, materials on human, on environment, but we need to study more about the long-term effects of these, nanomaterials in the environment.
Hmm.
So we need to do more research on long-term environmental and health effects of these, nano materials.
Yeah. Uh, so next question I want to ask is about PFAS. What does PFAS stand for, and why have these chemicals become such a big environmental issue?
Yeah, PFAS stands, for per and polyfluoroalkyl substances. When we talk about, the first thing is that they are man-made chemicals, meaning that they are not available, naturally. So when we make something, we use it, and after a while, we find, their, let's say, environmental and health, effects. So I think 1938 was, the first year that, this material were actually, used. And then after that, so we found, many, materials in this, family. Right now, more than 10,000 materials are in this, family. So it's a huge, let's say, family. So they use everywhere. So as a very simple, clue and key, if you have a non-stick, if you have a thermal resistance, if you have, oil resistance, if you have, if you use these materials, probably they have PFAS materials. So they normally use, in this, so in most cases, non-stick, pans includes, PFAS. So if you use, this stain resistance, shirt, probably it has, PFAS. So they use, in different, let's say, products. But the problem is that they are very persistent, and they can remain in environment and, in human for many years. And they have been connected to several health issues, such as, different cancers and, let's say, these health, concerns.
Yeah. Well, so is that why PFAS are often called forever chemicals? And when it comes to these forever chemicals, they are a growing concern when it comes to sustainability and clean drinking water. Why are they often called forever chemicals?
Yeah, that's actually a great question. So they are very persistent, materials. So we need something about 400, I think 50 kilojoule per mole to break down, the PFAS, materials. Uh, uh, Carbon and fluorine, bond, something about 450, kilojoule per mole. So this means that this is very huge, energy. So this means that, we can't remove them naturally. When you leave a, pollutant in the environment try to decompose,
Hmm.
this pollutant, by, microorganisms. But when you are dealing with this, complex, and let's say persistent material, it's really difficult to remove them, naturally. So what happened? They remain in, environment for several years. This is why they call, forever, chemicals. So And then I explain, they relate, to some, health and, environmental, issues. So when they remain, in environment, they can be transferred from, let's say air to water, then, from water, for example, to human, and then they can remain, for several years. So in some countries, we have, two types of PFAS. We have short chain PFAS and long chain PFAS. In several countries, such as US, using long chain PFAS, such as PFOS and PFOI, which are two main, PFAS, they have been banned, so due to these, concerns, these, environmental and health concerns.
So, can you explain in simple terms how your silver impregnated carbon material captures PFAS, PFASs, and what makes it more effective than conventional methods?
Yeah, sure. That's a great question. To explain, this actually question, I would like to refer you to this image, which is, our latest, publication in this field. So here is, the nanomaterial, in this case, activated carbon, and this is, the a short chain PFAS. So just as an, example, I explain, they are very persistent because these bonds C and F, this is really, we need a huge energy to break down, this, bond. So as you can see, this PFAS, material, which is a short chain PFAS and with 4 carbon, it has some fluorine, tail, and then one, in this case, sulfonic tail. So when we want to remove this material and we use, for example, activated carbon like this, so this fluorine tail can attach to the surface of activated carbon, and they can remove, from water. So we can remove them, from water by using, simple adsorption. Now, what happens when we introduce silver nanoparticles? This, small light dots are, silver nanoparticles. So when we introduce silver nanoparticles, they make surface charges, positive surface charges. So PFAS has negative tail. And these positive surface charges generates new sites to adsorb PFAS and to remove them from water. So as you can see here, for the nanomaterial activated carbon with silver, we have two methods to remove PFAS. So one method is by actually this negative sulfonic tail, this one and this one, and the other one is by a fluorinated tail to the activated carbon. So what happened when you compare these two material, this is the bare activated carbon and this activated carbon with silver nanoparticles. So this silver provide a new, let's say, sites to remove PFAS, and then they increase the adsorption capacity of the material.
Hmm. Well, so what is the future of this work?
That's a great question. We need to work on making, more stable, silver impregnated activated carbon. I mean, we should be able to use, this material for several cycles. So we need to use them, we need to regenerate them, and we need to repeat this cycle. It doesn't make sense to use just this material for one cycle. Why? Because they are very expensive. So we need to be able to regenerate them and to use them for several cycles. So we need to work on making more stable, nanomaterials. Moreover, we should think about increasing adsorption capacity. This improves, the adsorption capacity of, PFAS about 80%, but it's still low. We need to work on, making nanomaterials with higher adsorption capacity. And moreover, we need to do research, on health and environmental effects of, these nanomaterials. I mean, it doesn't make sense to make a new problem to remove, to solve one problem,
Mm.
right? So we need to think about the long-term, effects of this, material. And then the last thing is that adsorption is a short-term solution to remove PFAS. This is a physical process. We have PFAS in water, and then PFAS is transferred to the surface of, these nanomaterials. Then we need to remove PFAS from the surface of these, nanomaterials, and we need supplementary, processes to remove, PFAS. We should work on long-term solution. I mean, on destructive methods to remove PFAS. So these are, let's say, some future works, in this field.
Awesome. Well, Sayed, thank you so much for taking the time and for sharing your research and your insights. And I hope we can continue the conversation down the road.
Yeah, sure. Thank you so much, for having me today. And then again, thank you, for your interest in, my research field. And yeah, sure. Thank you.